All right, welcome, co-seated honors and preparatory students. Today is an interesting day because one, I am not there, so you will be learning entirely video lecture from me today. Thank you first and foremost to the sub who is taking over my classroom. You have some awesome TAs, and this is a great batch of kids. They're very diligent, they're very hardworking. They'll love to have fun too and joke around. Please note that after today's lesson, all right, there should be ample amount of time to do workbook problems, and I will remind you at the end of my lecture. Students can pick up extra printed copies if they didn't get it last Thursday or the last class that we met. There should be a couple extra copies, but they are limited for both the Unit 3 notes and the Unit 3 workbook set. If we run out of copies early, that is the student's responsibility to, for right now, download it on Notability and then maybe print later in the library. And when I return, or maybe later during lunch, the student can print the notes themselves from my website or Canvas. So that being said, thank you so much. And let's go ahead and get on with our lecture today. We will do about, I'd say 35 minutes of lecture on ionic bonding, one type of bonding in our new unit, Unit 3, on how do we connect atoms, what types of molecules can be made, and how do we categorize them. And then you guys will have ample work time. And then tomorrow, you guys will do a similar situation where you listen to a video lecture and you learn about the other two types of bonding. And what will happen then is tomorrow you'll spend the second half of class or whatever time is left doing practice and preparing for your quiz that is immediately approaching on at least on Thursday for 2023 spring class. It will be the next day after we finish our lectures on bonding, and it will be the day that I will be returning from my time away, and I have that already ready to go. So that's just a quick little plug-in for please pay attention, do not zone out. The sub, no student should be on their personal devices. iPad should only be being used for notes. I have a couple students that use their laptops. Just do a friendly reminder for them to stay following. If you notice they're not typing for a while, that's a problem. And no AirPods. And if kids need to use the bathroom, please send one out at a time. They have to leave their phone and they can use this pass on the side of my teacher desk wall. And the kids know where that is now. They're welcome to have scratch paper or grab any chargers from the first drawer as long as they return them. Okay, I think I did all the intro that I need to. I hope you all had a fabulous 4-day weekend and spring 2023 class, and let's go ahead and get going. So where we left off was we finished out Unit 2, and now we're moving on to our next unit, connecting atoms or building molecules and compounds. Our phenomena is a little bit more abstract this time, and it's going to simply be the compounds that we see in this world. And I did, however, end class with quite the gaseous demo to start having you guys think about how our general periodic trends that we've been studying are actually observed when we think about how compounds react. Because we know, generally speaking, the higher the Coulombic attraction, right? So previous knowledge says higher Coulombic attraction, okay, theoretically more reactive, okay? And we know on the periodic table, Coulombic attraction increases across and up a column, across a row and up a column, creating almost a diagonal effect where fluorine is considered the most reactive. Okay, and I can draw that a little better. Where fluorine is considered the most reactive. All right. Oops, there we go. And there's fluorine. All right. So that's what we've been previously talking about. And we also know that there's some, aside from the trends, there's just some particular columns, particular elements that are highly reactive. And those are the alkali and alkaline are quite reactive, the first two column of metals. And the halogens, okay? Column 17, right before the noble gases, we also know are particularly reactive just because of the nature of the chemicals. So what we did is we looked at a demo where we had a series of metals. We had lithium, we had calcium, we had sodium, and we had magnesium, okay? And I'm going to switch these around. Move these over because that was, I believe, the order of the demo on the day. And what we noticed is that the lithium was reactive and it produced a gas, i.e., a hint that a new compound has been made, a hint that there's been an exchange of electrons. And we would expect lithium to be reactive because lithium is a first column alkali metal. We then looked at sodium, and sodium was really reactive. It also produced a gas and it caught on fire, okay, with itself, which also makes sense. We would expect it to be reactive because it is a first column element. But it's kind of interesting that it was more reactive than lithium because it technically is in the third energy level. It has electrons in the third ring. It technically, according to our trends, should have lower Coulombic attraction slightly, and therefore a little bit less reactive than lithium. But we saw that it was almost appeared to be more reactive when it caught on fire, almost a spontaneous self-combustion. Okay. Calcium was a slower reaction. Okay. But it also produced the gas, and it actually produced quite an ample amount of gas. Okay. And calcium is a column 2 alkaline. So again, it makes sense that it's reactive, not surprised. And then we did magnesium and we saw no reaction. Nothing happened. So what we're seeing here is that our trends make things make sense, but then we also see there's something unique about the elements themselves when they bond with a given compound or a given other reactant. So in our case, it was water, all right, that also is just unique to that element that maybe goes outside of the trends, even though the trends are a great predictive tool. They're not perfect. So let's start talking about, well, what types of bonds are out there and how can we get more precise and accurate in our bonding predictions? So first and foremost, you have to understand what the purpose of a chemical bond is. So a chemical bond is the coming together of two atoms via electron sharing or exchange. Okay, via electron sharing or exchange. It's the coming together of two atoms via electron sharing or exchange. And we already know that there's a general rule that kind of guides us, but this is the official introduction of it. And we say the octet rule. Most all atoms want 8 valence electrons. And I actually should probably say want access. Okay, access to 8 valence electrons. And remember, our valence electrons are the electrons in highest energy level, right? Or outermost ring. Highest principal quantum number, if we're talking in the quantum mechanical model, right? Highest row, right? And so this is a rule that generally guides us. Now, I really want to point out the rule, right? The word I used here, which was access. That's going to matter later. We also, of course, know that we have a couple special conditions with hydrogen and helium, all right, being an exception to this rule. Only want access to 2 valence electrons, okay? So that's what we know, and we're kind of already familiar with this idea. Like, things want to be like the noble gases. Okay. Except for hydrogen and helium. And hydrogen and helium are okay with only having 2 because that's all they can handle. And that's why we put helium above the noble gases, even though it doesn't have a full 8. It acts like a completed atom, right? And the whole reason that we see this happening, by the way, is because having 8 or 2, depending if you're hydrogen or helium, having a complete, outer ring brings energetic stability. So the ultimate goal behind bonding is to bond in order to achieve maximum stability through lower energy arrangements. So theoretically, your bonding should always allow your compound or the atoms involved in making the compound to release energy. Kind of like in any type of friendship, you want to be around someone that stabilizes you and allows you to exist in a non-energy sucking way, right? We always have people that are like, wow, I like to hang out with them, but man, I just feel so tired after being with them. I might be one of those for you as a teacher, right? And your goal is, in how we think about atoms, is we want to think about atoms looking for the correct type of partnerships and bonding that leads to greater stability and lower energy exertion overall. Okay. So our first type of bonding that can occur is called an ionic bonding, or making ionic compounds. Ionic bonding, which makes ionic compounds. Okay, that's how we identify them. So I want you just to take a moment and pause me for a second in the video and look at these 3 examples of different types of ionic bonds. What do you notice about the elements that are being paired together? What do you notice about the naming format? What do you notice about the written chemical formula format? And try to identify some characteristics and patterns across them. And then resume me when you've taken about 2 to 3 minutes to do that with a partner. All right, so hopefully you guys notice some interesting things. First and foremost, some things I want to point out is that you should notice that we write always the name of the compound with an IDE at the end of the second element. Okay, that IDE represents something. Having an IDE after the second element tells me that these are not just 2 separate chemicals I'm just naming, like Sally and Barbara, right? These are Sally and Barbara Johnson, the same family. They're not just 2 random atoms together, not 2 random people together, but they're somehow connected. So what I like to say is, I'd like to make a bond with you. I'd like to make a bond with you. As a clue, as with the IDE suffix after the second element in a bonded pair, that they are indeed connected, not just separate listings. The other thing that you might have noticed is that we always put the metal, or the leftmost atom, the least electronegative, most likely cation, or not even most likely, it is the cation, okay? The more positive, okay, cation, positively charged atom first in both name and formula with the chemical symbols. Okay, so the least electronegative atom is first in both name and formula. So then we say that the more negative, more electronegative, more negative anion, a negative ion, anion is listed second in both name and formula. Usually, this is just a pattern that we're seeing across the 3. You also notice that when we look at them, sometimes we have a 3, or what we call a subscript. A subscript is a small number in the corner. This tells us how many atoms are in the compound. So for aluminum chloride, for some reason, to make this compound, we need 3 chlorines, okay, bonded to 1 aluminum. Okay, interesting. Also notice we don't write ones. We just assume that if I listed the atom at least once in the compound, there's got to be at least 1 there. So let's now move on to Okay, what's the official breakdown of ionic compounds? Well, the first characteristic is that here atoms bond by transferring or exchanging valence electrons, which means that each atom carries a charge. Carries a charge, okay? Each atom carries a charge. So we also see the role of electronegativity playing a part in this, and we say that more electronegative atoms and least or really low electronegative elements pair up. Okay, so we see opposites track, really high and really low electronegative elements pair up. So what we say is we're going to look at each part of the pairing one at a time. So we're going to first look at the first part of the pairing. We're going to look at our metal cations, which is our low electronegative elements. Okay, and metal cations are always metal. Okay, they always take on a positive charge and therefore lose valence electrons, which by the way makes sense from our unit 2 overview of the periodic table, how we said metals tend to lose electrons when chemically bonding. So we're seeing it all coming back to us. If we think about the electron configuration of cations, metal cations, what we see happen here is like sodium in column 1 will always lose 1 electron. So what will happen is it'll become 1s2, 2s2, 2p6, and we take from the valence shell, the highest energy shell, and we remove that 1 electron in the s orbital of row 3. And this means now sodium 1 plus, sodium ion, sodium cation now has the same electron configuration as neon, which by the way is a noble gas. Notice we don't lose our identity as sodium because we're messing with electron count, but we're keeping the same number of protons. So we are keeping our identity. We're still staying sodium. But what is interesting is that electron-wise, it shares the same electron arrangement as neon, which is a noble gas, which brings us back up to that concept of all elements want to be like a noble gas. How so? Not in identity, proton count, but in electron count. All right. So, there are particularly interesting rules with transition metals acting as cations. Transition metals are unique because what we see is that transition metals, it's really unclear, right? We were even having a hard time with this in class earlier. Like, how do I know the valence electron count for a transition metal, right? Because the D block is a weird area. It holds 10 electrons, doesn't really fit anything. It's 1 energy level lower than what you think it is, right? When you're reading in row 4, you really go down to 3D. It's weird. Well, this weirdness carries on into understanding when transition metals act as cations. And what we have to recognize that transition metals are what we call multivalent. Okay, which means that they can take on a series or a variety of different charges. Okay, so what do I mean by that? Well, when we look at sodium, right, column 1, 1A, it makes sense that sodium would want to lose 1 electron to become like the noble gas behind it. Therefore, it makes sense that all elements in column 1, alkali, will always be a 1 plus charge. Similarly, column 2A, or I'll just put column 2, okay, want to lose 2 electrons because they want to become like the noble gas that's closest to them, which is behind it. If they try to become like the noble gas in front of it, they have to gain a ton of electrons. It's easier just to go behind. Kind of like when you're riding an airplane and they tell you, look for the nearest exit. It may be behind you. Same idea. Okay. So we say that all alkaline elements take on a 2+ charge. There's some predictive patterns. You go all the way over to column 13. You'll see that these elements want to lose 3 electrons. So they always take on a 3+ charge. You go to column 14 and you see that these elements can gain or lose 4 electrons because there's no place advantage. All right. And then you go to column 15 and you'll start seeing a transition. Now these elements are closer to the noble gas in front of them. So you'll see they'll gain 3 electrons. So these elements take on a 3- charge. This becomes a plus or minus 4. And then column 15 will become a -3 or 3- charge. Column 16 will become a 2- charge, and your halogens, okay, column 17 become a 1- charge, right? And all of it makes sense if the idea is we're trying to get as close to the noble gas as possible. We can have a set charge identity with elements in the same column, right? Elements in the same column have similar properties as they work to exchange electrons in a way that helps them get like a noble gas, the same electron configuration. But transition metals are different because it's not really clear whether they're closer or farther away from one noble gas, and there's a simple solution. Instead, what we say is that they actually don't have a set charge that they take on. We have to tell you the charge. And the way that we communicate a variety of charges it could do is through Roman numerals. And Roman numerals are these little things that you see in front of books if you ever read them. That was a little bit of a jab, but to be fair, I don't read many books, but I will make it to the table of contents. And what you'll see is often in old school traditional books, they represent their chapters, the table of contents using Roman numerals, where we would say, okay, 1, 2, 3, 4, 5, 6, 7, all right, and so forth. And what we say is because transition metals are so unique in the fact that there's not really like a set pattern of what charge we can predict that they'll have, we say that we had to tell you. So we'd say if I wrote a Roman numeral 1 behind the name of a metal, transition metal, I would be telling you it's taking on a 1+ charge, or a 2+ charge, or a 3+ charge, or a 4+ charge, 5+, 6+, 7+, and so on. Okay. And so the trick is, why does this matter? Well, here's why. Okay. When I get a ionic compound where I have a transition metal serving as the cation and it's paired with a negative, more electronegative anion, what I see is that, for example, iron oxide, I have iron 1 oxide. So iron 1 is iron with a 1+ charge, and iron 2 is iron with a 2+ charge. Okay. And what I see is that they technically have the same name. If I got rid of that Roman numeral, I am iron oxide in both circumstances, but the charge makes all the difference. Iron oxide with a charge of 1+ turns out to be 2 iron atoms bonded with 1 oxygen. But iron 2 is 1 iron atom bonded with 1 oxygen. So even though their name sounds the same, they're very different compounds. They're a different type of combination. So that's why with transition metals, it's really important that we do specify the Roman numeral, okay? And down here, this compound, this different combination of iron, okay, oxide, it is also called iron oxide, but notice the charge would be iron 3 oxide, okay, would be the name. And notice having a 3+ charge creates a entirely different combination, a entirely different combination of atoms, therefore different compound with different properties. All right. So that's just a little bit about the cations. Let's move on now to the anions. So the anions are usually always nonmetals because nonmetals, as we know, like to gain or share electrons. So we say nonmetal anions are always, okay, a negative charge, right? And this occurs through gaining electrons, all right? And that makes sense again, because like I said in my little demo up here, when you hit the non-metal region, columns, 14, 15, 16, and 17, you start seeing that the noble gas in front of them is the closest one. So it would make sense that they'd want to gain electrons to become like the noble gas nearest to them. So let's look at sulfur, for example. Sulfur 2 minus, okay. Sulfur is a common anion. And what we'd say is sulfur has gained 2 valence electrons, okay? Which means that when you look at the electron configuration, it goes from 1s2, 2s2, 2p6, 3s2, now to 3p6. I have added 2 more electrons in the closest, most available orbital. So remember, p orbitals max out at 6. So I'm going to fill up the p orbitals before I just hop on to the next energy level. So I fill it up with the extra 2, right? Add 2 electrons and I get 3p6. Okay, add 2 electrons and I get 3p6. All right, and that means I am now having the same electron configuration as argon, which is, again, a noble gas. But I don't lose my identity because remember, I didn't mess with the proton numbers at all. So I'm still sulfur. I'm just sulfur with a particular electron arrangement that is more ideal, more stabilizing. Okay? And for the most part, there's nothing really special about anions. We don't have any special categories. We don't need Roman numerals with anions. But we do, however, tack on the anions, we add IDE for the last syllable. So oxygen, when it serves as an anion, becomes oxide. Sulfur, when it serves the role of an anion, becomes sulfide. Okay? So that is something that is special about nonmetals and their naming, okay? So how do we now put these 2 parts together? Well, the first thing that you have to recognize is that when we put together an ionic compound, the stable ionic compounds always have their anion and cation charges canceled to 0. So I'm going to actually rephrase that as cation because it goes first. And anion charges must add up to 0. So what we say is the superscript is the charge value, and we don't write that. We don't write in the name, okay? But we do track it. What we do is we do track it to predict bonding, okay? But the subscript, however, which I've already kind of told you about, is the small number on the bottom. And this tells us the number of atoms required, okay, to have charge cancel. Okay, we could say it's like the ratio of atoms in a compound. Okay, so that's the biggest rule, is that when you're building or writing out ionic compounds, you got to make sure that their charges cancel to 0. So when we look up here, notice iron 1, okay, means it has a 1 plus charge, but oxygen always takes on a 2 minus due to its placement in the periodic table. So why do we need 2 irons, subscript 2 atoms of iron to make iron oxide in this particular transition metal? It's because what we see is 2 times 1 equals 2. And when it's added to -2 from the oxygen, we get a charge of 0, telling us we have a good ionic compound. What about the one below? Iron 2 plus, oxygen 2 minus. Why do we only need 1 iron for every 1 oxygen? Because 2 plus -2 is equal to 0. Iron 3 oxide, well, why do we need, okay, 2 iron 3s for every 3 oxygens? Well, it's because 3 times 2 equals 6, and -2 times 3 equals -6, giving us a total of 0, right? When we add all of these together. Okay? I know I kind of wrote it funky like a weird math problem, but you've already kind of seen it. I just am now explicitly telling you. So charges, though they're not written in the compound formula or name, they are what we use to predict how and which atoms will bond, right? So when you write the name, as I mentioned earlier in the warm-up, you always write the more positive cation first, plus the anion, plus IDE ending. Okay, so let's do some practice. Go ahead and try out these problems right now and pause me. Okay, so hopefully you pause me, and you should have gotten for this one, calcium oxide. Calcium has a 2+ charge because it's in column 2 alkaline, and it's going to lose 2 electrons, and oxygen has a 2- charge, so you're just going to need 1-to-1 ratio, calcium oxide. Next one is sodium oxide. Sodium likes to take on a 1+ charge. Oxygen takes on a 2-. That's why you needed 2 sodiums. But notice I don't tell you the amount of atoms in the name. Okay, magnesium. Okay, fluoride. Instead, not fluorine, but fluoride. I'd like to make a bond with you. Magnesium takes on a 2+. Fluorine takes on a 1-. That's why you need 2 fluorines. But again, I don't actually say the amount of atoms in the name. I just assume that you know the math, the charges. And then aluminum. Okay, chloride. Aluminum is a 3+ charge. Chlorine is a 1- charge based on their placement on the periodic table. Therefore, we need 3 chlorines to correctly cancel out the charge and therefore make a good ionic compound, giving us aluminum chloride with 3 chlorines. Okay, so now I just have two more things I want to introduce. And the idea is that we can actually have groups of atoms that act like a single ion. So these are called polyatomic ions, and they're a group of atoms that are together carry a charge. And so what we see here is we see a table of examples, like ammonium ion is NH4, and that NH4 together, those 5 atoms carry a +1 charge. Okay. We see nitrite that is NO2. So a nitrogen and 2 oxygens together carrying a -1 charge. And so what we see here is instead of having single element atoms carrying a charge, now we have teams or groups of atoms that act like a single charge. And so what we say is, one, when we write the names of them, it's really important for us to put parentheses around our polyatomics in the formulas so that we don't make a mistake. For example, if I have 2 sulfites in a compound, okay, let's say I have 2 sulfites in a compound, which would mean that my cation, according to the table, sulfite is 2-. It would mean that my cation must be a 4+ charge, right? If I need 2 of them. It's really important that I write sulfite, this group. I have 2 of them, okay? I have sulfite and sulfite, okay? I have 2 sulfite atoms bonded. But here's the problem. If you don't do that, if you just wrote SO32, it's like saying I have sulfur plus 32 oxygens, okay? It's like saying I have sulfur plus 32 oxygen. So that's why when we work with these unique grouply charged atoms, that we put parentheses around them, these polyatomic ions that together carry a charge, these group of atoms that together act like one single charge. If we find that in order to create good compounds and cancel out to 0, that we need a couple of them, you got to put a parentheses around the unit, the group. Okay. Sad news, you do have to memorize this by quiz time. So have fun. It's called Quizlet. Okay. And calling up a friend. So let's try some examples. What we have here is we have calcium connected to CO3. CO3 is carbonate. So this would be calcium carbonate. Calcium takes on a 2 plus charge. According to my table, carbonate takes on a 2 minus charge. So that's why we see a 1-to-1 ratio. And notice something about polyatomics. When we name them, we keep the polyatomic name and forget IDE. And here's why. Because the name itself tells me it's an ion. Like the name itself tells me it's a unique bonded group. Like I don't need to hint at anybody that I'm not listing a pure element. So that's kind of why. So next one is aluminum sulfate. Okay, notice I'm not telling you the number of atoms when I'm naming ionic compounds. I just assume you can do the math. Okay, and this makes sense, by the way, why we need 2 aluminums for every 3 sulfate groups is because aluminum takes on a 3 plus charge, but sulfate carries a 2 minus. So the common denominator between them is 6, so that my charges again cancel. How about the next one? We have lithium, our metal, always being named first, our cation, sulfite. And lithium is a 1 plus charge and sulfite's a 2 minus. So that makes sense why lithium, we need 2 of those to bond with that one group that carries a charge. So as you're seeing with polyatomic ions, we do the same naming rules, except for the most part, the only thing that changes is that we don't add IDE. We don't change the name of the actual polyatomic itself. So go ahead and try these practice problems and pause me just for a few seconds, and then we'll talk quickly about ionic solids, and then we'll stop for today. Okay, so hopefully you pause me and tried it with a partner for a little bit. And what you have here is hydrogen sulfate. Hydrogen, okay, takes on a sulfate is an SO4. It's a 2 minus. Hydrogen is a 1 plus. So what you would get is hydrogen with a subscript 2 sulfate. Calcium is a 2 plus charge, and chlorite is ClO2 minus. So ClO2. And because chlorite carries a 2 minus charge and calcium carries a 2 plus, we see that that is a good reaction just by itself, as is. Each individual ion together, 1-to-1. Next one is sodium hydroxide. So we see sodium hydroxide. Hydroxide is OH with a -1 charge, and sodium always carries a 1 plus, so that's why we only need a 1-to-1. And then the next one is sodium, and this is bicarbonate, and bicarbonate carries a 1 minus charge, so we see why it's a 1-to-1 ratio, so it becomes sodium bicarbonate. Okay, so the quiz that's coming up will be testing you on your ability to name and recognize polyatomics and write their formulas. All right. So quick note, ionic compounds, when they form a solid, we call them actually salts. So NaCl is table salt, but also by just simply saying the word salt, you're literally saying it's a solid ionic compound. Like that's what the actual name translates to. And so ionic compounds, what they do is they arrange themselves into one giant, okay, ionic compound with cations and anions. And particularly what you'll notice is that it's repeating units. So with NaCl, what we see is that the Na plus charge is being constantly surrounded with the Cl minus, okay? And what you see then is they will constantly arrange themselves. So they're positives and negatives are alternating, surrounded by the opposite attracts. So you're basically forming a giant ionic compound, and it goes into this like tic-tac-toe row column structure, like every opposite. Okay. And that's why we call it often a lattice structure. We often call this it creates a lattice structure, is what we say. Okay. So you have a ton of unit workbook problems in your Unit 3 workbook that you can find on Canvas or my website. Please spend the rest of the class period working on practice. You cannot understand this unless you just practice naming 50, 100 compounds. What you'll see is that the workbook is a little bit of a combo of tomorrow's lesson on covalent compound naming and ionic. All right. So do the parts that you can identify as ionic with a metal plus a non-metal or a metal plus a polyatomic. All right. And start also working on making flashcards of some sort and memorizing those polyatomics. We've started a new unit. So don't forget that with a new unit, the old unit, Unit 2 work is due by the time we test on Unit 3. So let's say you feel really confident about your naming skills right off the bat. You don't really feel like you need to make flashcards. You do a couple workbook problems, you feel good. You should not be wasting this time. You should be looking at Canvas, making sure you have everything in for Unit 2, any homework checks or so forth. All right. So your TAs are a great resource, and best of luck, everyone. Good job. Bye.